Thank you. So, as we discussed, it's a presentation from the whole team. The team is called Computer and Fluid Research Group. So yesterday I showed some numerical method, especially finite element method, to deal with optimization. And today I'm going to have a first introduction on deep reinforcement learning that's going to maybe replace or mimic some tools that I presented yesterday. And there is a colleague of mine going to pursue, when I finished, more information about deep reinforcement learning. I already sent the presentation of yesterday, so you're going to have it by a link or on the document of the course. And when my colleague also finished the course on deep reinforcement learning, you're going to have also some additional tools to download and play with it. So today is why we are interested in such branch of machine learning. I will show you some coupling with fluid mechanics, but what is interesting for you is the shape optimization. So like you have seen today or this week why machine learning is interesting in many situations. It can be used for predicting, for analyzing big data, and also can be used for optimization of different systems. Here is like a heat exchanger system, but doesn't work in that now. So, but the bridge between the machine learning world and the computational mechanics is ongoing. So there is a lot of things to be developed in this area. And why we are motivated in this coupling, because it can help us reduce the computational costs in somewhere, or bridge the gap with a method that we cannot solve classically. But there is some challenges. There is a high cost for data acquisition. There is multiple tests to do on the coupling, and maybe sometimes you can have limited access to resources. So if you look at it from a broader side, I think you saw some stuff on unsupervised or supervised this week, but today we're going to concentrate on this branch. So if you look how we classify them, like this activity, if you are looking for prediction, only simple prediction, you can use supervised, or you are using for example, segmentation or customer segmentation or clustering, you can see that unsupervised learning is good. But today, we are going to focus on reinforcement learning because it helps you take decision. It is well introduced with the game called Go to take decision on your movement. So you see my hand? This movement I showed them yesterday by a level set. So it's gonna take also some decision on the deformation of your shape, on the respecting a certain target and taking decision. So it learns and decide. Since this part of machine learning, it could be interested for you. It is now very well used for robot navigation, but we are using it for fluid mechanics. So how it works? You have an agent, like a guy, looking at your environment, okay? And your environment is actually in the state S, that means at the initial. So it look at it, and then it send a certain action. For example, the environment could be a chessboard. You take an action by moving a piece, and then you evaluate this movement. If this movement go into the direction that you need, I'm going to win the chess. So you're gonna have a reward. Very good. Continue in like that. So if it's not, you're gonna have a bad reward, maybe 0. So in this case, the agent will have a philosophy of having a cumulative reward to the best. So, okay, and by that he will learn later when he finishes to take the best decision for you. However, with the arrival of deep learning, we can assist this agent by a neural network. So the agent will since it's something to relate to learning, so the neural network will enhance the capability of the agent. So the agent will have like deep neural network capabilities, so he can handle bigger spaces or more parameters in order to check his movement and see if he's winning. So you can see it differently by this one. If a supervised learning, it will help you when it converges to rank the labels that best fit the image. Do we have a cat in the in the image, yes, no, okay? However, in a neural network, it will not be like the labels, it will be the rank of the action possible to perform in your state. So if you are playing a game, it could be, should I run here, or should I jump? Should I go to the left, or should I go to the right? So this illustrates how a policy in a reinforcement learning map your state to the best action to do. If you are in this state, how I'm going to move. And the neural network coefficient can be initialized stochastically or randomly, and then they will enhance to learn and to get you your last model. Using the feedback from the environment, the neural network can be used, can use the difference between what is expected to have a reward and what is a ground truth reward. That means if you are mapping a temperature and you have a gradient inside, you're not happy with it. And the learning, you should understand that it's dynamic. It's not like that you do a lot of CFD and then you do your learning and then you have a model and then you use it. No, it's on the fly. That means from the beginning of your computation, you start learning dynamically and it converges. I will show you some example. So look at this. This is a model that converges. That we change the environment and we see if the model understands his best action. The best action is like to go and to pick on the pink one. So this is a converge model, and since it's picking on the pink, that means this is very good. That's why it's getting a reward. Okay, so this is how we can explain the reinforcement learning. So what is happening? The episodes are changing until the convergence. Okay, and at the end you are maximizing the cumulative reward. So whenever you gonna ask it again, it will give you directly, as you see here, directly the best action. So the idea, even if you have these tools, and you can find these tools, but in this course I will tell you what are the bricks that you need to develop on your side in order to have it working. And there is only for you 3 questions. There is how to design the reward. What is a reward? It's the objective function actually of the optimization shape, for example. What are the action, the deformation you're going to take in order to have the movement of your shape? And the environment can be anything. And this is that replaced yesterday. It could be experimental, it could be numerical, finite volume, finite element. It doesn't have to know about how to solve the equation. So it's your environment. You're gonna hook on your environment and deal with it. So that's why it's interesting in this picture that I tell you that your environment now, it could be a Reynolds on 2,200, or I add a 0. It could be 22,000. So there is no revisiting the equation. There is no, it's like it is independent of what you're solving. All you have to do is to really couple the bricks together in order to have it. So this is a very interesting, and this is the message that I wanted to send yesterday. If you want to go higher in Reynolds number, or you're going to change the physics, you don't have to develop the adjoint from scratch again. You don't have to deal with the boundary conditions that are related to the adjoint, so you can replace them. I'm not saying that this is bad what I presented yesterday, but I'm saying that there's some applications that could go with this one, or other can go with the other one of yesterday. So again, I'm telling you that here I'm solving the Navier-Stokes equation like yesterday, but now I'm adding, for example, a Spallard-Armaras model. This is a turbulence model, and this is convection diffusion reaction equation. So just remember that this is time dependent. One, it has a reaction term additionally. So if I couple it with the system of yesterday, so I need to develop also the adjoint of this equation. Okay, so it could be a really complex task to do, and here there is no issue. It doesn't interfere with the system that's gonna learn and help me obtain the shape that I want. Okay, so now I'm gonna, if you are convinced on the environment, and I hope you are convinced on the environment, I'm gonna look on the reward part. So the reward part, it represents the objective of the control law that you want to do. Okay, so here you can feed it with what you are looking for, and it must be designed on case by case. It's not that complicated. It depends on the case. I will show you a lot of examples so you can be inspired. And the high value reflects of this reward reflects that you are going into the right direction and you are converging to your good system. So remember, it's a cumulative, so it could sum all what is happening for your reward, and you can plot it on your during your computation to see if it's converging. I'm gonna show you now, for example, if you want to reduce a drag on a cylinder, like a flow past a cylinder, all you have to do is to put minus Cx. Here I put Cx bar. Imagine you are fluctuating, so you take the average of Cx. So another one, if you want to reduce the lift on drag ratio, but you want to add a constraint, like, hey, don't go, like, change the form, do whatever you want, but don't go far away from the surface of reference. Okay, remember, in the drag we can lose the if we lose the geometry, there is no drag. So hey, pay attention that the reference is important. So it's like I'm adding a certain constraint to my reward. Okay, the other one is reduce the drag on three objects while they are turning. They have a rotation velocity, and I want that the sum to be controlled. No, don't go crazy. That means I don't have a budget for this energy to turn them, so I have a limited budget. So I put it here. And the last one could be related to temperature. Okay, I want to reduce, for example, the gradient of the temperature on this part. So this is W do times the gradient, and this is a part of the reward. So you can couple it with another part of the reward, and I want also to have a temperature homogenization, or a temperature field to reach a field, and this is W1. So you can combine, like yesterday when I showed you at the last part, when we couple with the thermal, several weight on each reward that you want to put. Okay, so this is how to construct a reward, and you have many examples to show later. Now the action, and this could be tricky, and this is maybe only the difficult part for you, because action, that means you're going to change your environment. If you are changing your mesh for your domain of computational domain, so you are deforming, you are moving something, you are like a chess, remember? So you need to have some tools to do that. It could be done by immersed boundary method, in fictive domain method. It could be done with a different approach. We use here the immersed method. Why? For example, if I want to move this cylinder, so these are actions. Okay, where should I put it? Where should I put it? Here, in this case, which angle of attack I should choose. So I'm changing my environment, and I have some tools that directly give me the new environment rather than constructing it from zero. Here, where should I put this point? Where should I put this point in order to have the minimum drag on my system, for example? And this is what you're looking for from yesterday. I'm deforming the shape. Okay, so you can don't worry, you can create with different tool like GMSH, for example. You can parameterize it, obtain the deformation that you want, create the mesh correspondingly, do the computation, then go back and deform it again or change it and create the mesh. Here I'm not creating the mesh, I'm just changing a function inside the domain and adapting the mesh to it, so it make me some economy on my computation. So there is an interaction, there is angle of attack, there is reducing the drag, there is optimal shape. So all that can be used for your action. So if you are convinced, I will try to show you the first example. So I'm putting here a point, like a small cylinder, surrounding a square, in order to see where is the best place to put it. Okay, so I prepare my system. I prepare this action. That means I can say the point can be anywhere you want. You can be smart by saying symmetrically, that means up or down as you wish. And then I click it on Monday morning, Monday at night, you will have your system converged. For example, he's running alone, all the computation and checking which one is the best, okay, and converging very fast in some cases to the best one, because he is evaluating the reward And whenever the word is not good, he will not go back to this situation and we choose another one. And he'll have a policy that is learning on your system what is happening, so it converts. So the best, I will not tease you more than that. The best situation is this one. Okay. We knew in advance that this is the best situation. It is known this test case, but we wanted to see if the system learns it. And when it's learned and put it at the right position and the right distance from the square, you can see that at the end we have 30% of reduction. So this is very, very important. Okay. So this is the example that you were waiting for yesterday. How we gonna deform a shape? Okay, there is a different way. I understand that you saw something this week on that. So imagine you have a shape and you can parameterize it by control point, and between the control point you can insert, if you want, some NURBS or some polynomial function or whatever you want. And also, if you want to reduce the number of parameters, you can say what happens there up should be happened down. Okay, that means your shape, you want it from the beginning to be symmetric, but this is a choice, but no, there is no limitation. And by fixing the points at the front and at the end, you can also fix your chord. I don't want to change this shape, I just want to change this shape. Okay, so really you can configure the test case that you want, and then your system will handle this blue point, this point that you can see here, in order to respect your objective function. My objective function here, for example, it could be not lift on drag, could be only drag, reduce the drag, but don't go far away from the reference surface. Okay, we use in our case cubic Bezier. Okay, and we have 6 control points, and also mesh adaptation just to enhance the simulation. So I can run now from 20 to 5,000 without even care if the system should handle an adjoint on the turbulence model or not turbulence model. So we can do it without any issue. So this does to show you that no need to learn aerodynamic before running this computation. There is no need to do computation in advance in order to learn. It's on the fly. It will try, and you will see your shape is advancing. Okay, so these are the shapes that you can obtain, and we are happy that directly on Reynolds 100 it find a very good shape, right? Like beats any shape that you can see, but as you see here. So now I want to do a real application, which was demanded by people. It's to work on the given a very tough, I'm looking at the conversation. Yes, very good question. There is a question about ventilation system. I will answer it like that. We worked on a turbine that it has two blades, and we need to optimize the 2 blades, okay, from left and right, in order that the system will have more efficiency. So you can add as much as you want, like geometry like that, in order to form your different ventilation system, and each one is controlled. It could be symmetric for 2 and free for other 2, so you don't have the symmetrically for the force blades. And I hope I'm gonna show you an animation on that. I don't have it here. It's like you remind me now. Maybe I can send it later. So we put it at the angle of attack of 30. We are challenging it if it can see, if it can do a good shape in this direction. So this is a tough example. And what you are seeing here are how the word is converging, okay, in respect of number of episodes. Maybe it's easy because Reynolds is low. Also, how the surface is like respecting the surface of reference. And this is the animation that you can see. I'm putting all the series of of results, one after the other, to show you from the bad reward to the best reward how it's converging. And what is important is here that at the beginning it's changing a lot because it's finding itself, but when it converges, he's smart. So it's like it trusts. The movement are very small to make sure that I'm good or no. So it tries a little bit and then it converges. So if I go higher now to Renault 5000. You can see that the system is also converging, but with a shape that is more like aerodynamic. That means very small down there and bigger on the shape. So we were very happy about it, and we tried it in 3D. In 3D we were very how we say it, just we wanted to see if it worked in 3D. So what we did, extrusion. That means we made an extrusion of the geometry, and it is the same shape everywhere. So we can go and parameterize every part of it, okay, and then do interpolation of the geometry from one section to another section. We didn't do it here. This is a complete section that is deforming, okay, but we can evaluate it on one part of the section, another part of the section, third part of the section. This is one way to do it. There is another way to do it. It's to do it in 2D, extrude it, and evaluate the simulation in 3D. Say what's happening in 3D as a average drag or average lift on drag. Give it back to your system in 2D. Do the simulation, do the learning, get an action, that means a certain form, extrude it, do the simulation in 3D. So what I'm telling you, that the flexibility of the method is very impressive, and it depends really on the application if it fits or not. So so this is what happens in Renault 5000. I can show you the animation. So what is you are seeing now is the 3D flow on the whole section, okay, and the deformation is made only on one section. And again, if you parameterize your wing, this is very good for wind turbine. You know that the wind turbine for windmills, it has different NACA profile on every section, and then we interpolate them together. So you can do the same in this one. Just one second. Okay, and this one was the most impressive example. We have to turn 3-cylinder. This is a very challenging example. Everybody is trying to do it. What the good news is, we are using here U-rounds. So remember rounds, that means unsteady rounds, unsteady, and you need also.
Professor Hashem, can I ask
Yes.
a question?
Yes.
I want to ask you about the neural network, how it look like, and how is the same neural network for 2D and 3D applications, or
Yes.
you change it as well?
No,
so
you don't have to change it from 2D to 3D, and the neural network could be simple. You will have these details in the second session. Okay,
okay,
the neural network could have only 2 layers or not that expensive. Now it depends if you are doing single step or multi-step. If you are doing optimization like I'm doing here, it could be simple. He can learn very fast. But if you are doing control, okay, you need to feed it information also from your environment, not only the rewards. Like here, it taking a reward, gives you an action, reward an action, but you can feed it with the pressure involvement surrounding the wing. You can feed it with certain points that are related to your flow, velocity flow, and this go into your network. And your network could be here a graph neural network if you want, or it could be a very tough network, okay, that is learning on what's happening. But remember, this learning it is used to decide what are the actions, okay, based on the last reward that I obtain. So you will see all the details on the architecture after in like 15 minutes. Okay.
Thank you.
I'm showing the motivation just to motivate you about this method. So here we're gonna turn 3 cylinders. So I have 3 parameters on the no more than 3 parameters. We have the velocity and also the direction. Okay, but again, don't let your system go crazy. So like me, you can give the action interval and an interval, so you cannot go any behind it. If you are doing a shape, for example, you can limit the movement not to go 10 meters above or 10 meters down. So it's really nice to know about your simulation in previously before starting, and gives the right intervals for your action, so he can use this interval in order to give you the optimization. So I'm going to show you now how the system converges on the rotation velocity for each one of them. Okay, on how we can see that the reward is going down, and you can really see that there is a reduction of 60%, and you will see now the difference between control and uncontrolled one. So what is happening on the control one? It erases all the vorticity behind the cylinder. So he knows what are the right configuration for the rotation and the velocity for each cylinder, in order that when the flow passes these guys, no more vorticities. Okay. And this is the last configuration. So what I'm saying that if you compare the wing deformation to this test case, you can see that the huge difference between the application, and it's a huge difference in the application. You cannot really see it by my presentation yesterday. The example was very close to each other because the system that I designed were, for example, steady and was not turbulent or could not go that far. So that's why the multitude of application here is very important. So this is the last example, which is very interesting. It concerns really the industry that are using it today in France. So this is a part, okay, it's like an illustrative example, but it is now designed on real furnaces. So I put 15 centers in order to evaluate the gradient on this part, and I have different scenarios. The first one, where should I put the inlet 1, 2, 3, okay, in order that the gradient to this part is minimum, and this is the 2 outlet here. So, and I'm adding a constraint, the constraint that the first inlet can only work on here, the second one can work on here, and the third one can work on here. So this constraint, where do you put it? Should you put it in the reward, or you do it by construction? By construction, because when you give the interval of action for each inlet, you can say this first inlet, you can work here. So what I'm saying, that there is a part of some constraint and limitation, the restriction that we talked on yesterday, that you can put them in design for your system, rather than putting them in the reward for your system, in the cost objective function. Okay, and this is the global difference also. So do you agree with me that if you have an inlet on the close to the shape here is not good, close to the solid, so it will avoid it. So you will see that the scenario like that are not good, because the flow here is so close and creating gradient. So what is happening is trying to find a best situation. Impossible, no, not impossible. It's very hard to do it in using other methods. So this is a converged system. You look at it, it's not changing anymore. It's symmetric, by the way. It's left or right. Let's put this situation. What is happening? That the first inlet, it uses its interval to get the far away maximum from the part. So it put itself here on this side. And then the other one that is here, he said, oh, I need to compensate. So he will use this interval to get closer to the part. By doing so, they will create streamlines that are circular surrounding the part, which are responsible of having a gradient that is homogeneous, or gradient that is low inside, temperature homogeneous, and gradient very slow, very low inside the part. And the last guy, he said, oh, I'm gonna not disturb you, I'm going to do like you, I'm going to put my back on you and then go out together without any issue. So why is important this example? Because it's a coupled system, dynamic system, coupling heat transfer with Navier-Stokes with a immersed solid. That means there is a solid, there is a fluid. Okay, so two phases communicating to each other. So that's why I'm saying it's the strategy of using deep reinforcement learning in this case, it's like worth doing it. And the last example for you is to tell you that you are changing boundary condition. And it's easy for you to change boundary condition. You can put boundary condition here, you can put boundary condition here, so it's only a flag for you, and you are changing boundary condition. So there is a change of boundary condition, there is change of boundary condition that rotates and direction, and there is a change in the form inside the geometry. Now, if I do the same example, I remove the constraint that the inlet should be in a certain interval. Look what happened. You can deduce it before. You will say it will choose how to create a perfect symmetry of the flow inside the inside your domain, and this is what it's doing. This is the configuration that converges. You see it converges, and if you look at the part, it's perfectly homogeneous. There is a perfect symmetry in the domain, and more than that, if you are designing a system, here it tells you you don't need 3 inlets, you only need 2. So what is happening is he's superposing the 2 inlet one on each other. That's why we have only 2. However, I can tell you it's lazy. Why it's lazy? Because we didn't insert here, hey, if you are far away from the part, the cooling or the heating of this part will be slow. So what happened? It's like we are telling it, we need to add in the reward another aspect that is related to, hey, I need to be heated or to be cooled very fast. So I'm worried not only on the gradient of the temperature, I worry on the temperature, to have a temperature of reference, for example. So in this case, maybe it will get in them closer to the part and have at the same time homogeneous gradient, homogeneous temperature, that means no gradient, and high temperature. Okay, so you need to modify your reward for that. So now I inverse the strategy. I have a design, and I need to optimize this design by putting the part in a place that works. So now I'm moving the part. I have a design that works very well, symmetry. Do you think he will retrieve the symmetry? That means that the cylinder is in the middle. That means the part is in the middle. Yes, the part in the middle, it's a good minimum, but not the best minimum. I will show you. If it's in the, look, it shows it's a little bit shifted. You see here, this is a 0, that means the center. I shifted a little bit to say that in the center, you will have symmetry from left to right, but there is no symmetry from up to down in your system. So you need to shift a little bit in order to retrieve streamlines that will have a global recirculation on the part. And it chooses to shift it, and that means it is aware of your environment, that your environment surrounding the part is better than the other one, and that's why it chooses this one. So it's like an enormous result in this case, because a little shift that do that much effect, if you can interfere in industrial application like that on many process, you can really do an impact. Now, I told you that, okay, this is very good for the gradient. Can we do better? Can we have something related to the temperature? That means I need to have the temperature high. That means I want to have an economy on my gas in order that the part go up in temperature rather than putting the burners very far. So I need not only that the part will be homogeneous in temperature, but also to increase in temperature very fast. So this is a very complicated one. We published it. It was a preprint last year, but it's now getting out. It's published. Look what happens. So the parameters here are X, Y, theta, angle, the flow rate of the three inlet, the position of the three inlet. Okay, so it's a very complex situation. Okay, in number of parameters, and two rewards or two objective functions. One is related to the homogeneous temperature, and one is related that the temperature will be high. The result is crazy. Look at the result. This one. It was not afraid, the system, to take the part and push it close to a burner. When you push it close to a burner, you create a gradient on the left side immediately. But by doing this, also the flow will be deviated, and by controlling the flow rate from left to right and the position and the angle, it created a very nice structure of the flow that surround the part in order to have fluctuation better on the other side to compensate the burner from the side. And you can look at it and you can feel that it's already homogeneous temperature, and you can understand, since it's close to a burner, that going to be heated very fast. So that's why I'm saying orientation, position of the inlet, position of the part, flow rate, heating speed. So when you are at this complexity, okay, these gonna change all your cost function in your classical homogeneous system, if you are doing it with the classical adjoint approach. And that's why I'm saying here that it could be nice to use that. Somebody asked me before, is there an issue to change something from 2D to 3D? Nothing. Only your environment will change from 2D to 3D, and feed the information to your system. It's not, if you are a drag, it's not a 2D or 3D. You feed the information to your system and it changes the system correspondingly. And here I'm showing the position convergence of every one. 1, 2, 3. And you can see that the part is homogeneous. This is more complex situation. We're not publishing it. We'll publish it soon. Like we have even boiling on the part, and we choose the orientation of the part. I mean, this system can beat any. And it's impossible to do it maybe in adjoint system. Maybe. Okay, this is a real example from NG. And somebody asked me the question: how you do the control? How you change your neural network? Here I change my neural network because it's a dynamic situation. I'm feeding it with all these additional points. These additional points will be the input of your neural network. It has a image of your pressure and velocity in this region, and it doing a control by two small feeder that interfere in the flow in order that the drag of the system will be low. I will show you no control with control. This is a true application because we are showing all the details. Maybe not all the people show the details. Here we are showing the detail because you will feel it. Look at them. No control, control. And when I click like that, it starts the control. You can see the two feeder down there. Here, you can look here. How it's doing all this situation in order that the drag past the cylinder will be elongated. You see? Yes, now. And now the system learned. So if you insert a new cylinder, it will handle it directly. Now this are the phase of learning until it converges. So conclusion, I'll show you what is important for me to understand the coupling approach for the actions, to take them, how you change the environment, how you choose a reward, and how you design the environment from the start. I show you some example on flow control, conjugate heat transfer, and wing shape optimization. And know that all that is not made easy. There are a lot of students working with me in the group, and there is that also can be related to application in bio, to how to design patient-specific treatment for people, and there is I have an ERC on this subject. So what is going to happen after the break? Jonathan that worked with me gonna show you all the details that you asked about the construction of these guys. And I'm going to use the 3 minutes that I have for questions.
Hello, can you hear me?
Yes.
Fine. It seems for me that you're using these techniques just to solve optimization problems. So in this scenario, it's important to use the reward instead of the cumulative reward because you're using just a loss function.
Yes, if you are doing a single step, yes. So you are looking for the reward that converging like that. Okay, but if you are doing control, that means it's very hard that you are doing a control on shape optimization. That means you want really that when you are swimming, for example, or you are flying with a plane, that changes the whole time the shape, okay, to correspond to the hitting air, for example. That is a very rare situation when you need to do shape optimization for a control system. But for an optimization, yes, like you said, I want the last design. So you let it go and you obtain the last design, and this design they're going to use it later. So the last design in this case is this one. Is this one. Okay.
Okay, thank you.
Who was first? Yeah, maybe I walk up tonight.
Thank you very much for your nice presentation. Just one question. Have you employed reinforcement learning for topology optimization as well? So you showed examples of shape optimization. I was wondering what happens in that regard.
Yes, we are doing it now, different way. I will give you the idea, but don't go publish it tomorrow, okay? You saw yesterday that the shape optimization is related to beta, that is like pushing the geometry to form. This beta comes from an equation, or it is inserted in an equation. Our idea is to do like what we call physically informed reinforcement learning. That means rather than going and directly interfere with the shape that you are seeing here, geometrically speaking, we are willing to interfere in a parameters of an equation. Okay, if you have a convection diffusion reaction equation, it has a convection magnitude, it has a diffusion conductivity, for example, and has a reaction coefficient. So our idea is to go and interfere on the parameters or the coefficient in a PDE equation, and when we solve this PDE equation, we get this velocity. So rather than interfering on geometry, we will interfere on an equation, okay, that give us the result of the equation, give us the needed shape movement, deformation movement that we're going to put in the level set. This is our idea.
Thank you very much.
Yes.
Hi, I have two kind of related questions. The first is, do you know how sensitive your results are with respect to the turbulence model that you choose?
Yeah. It's really a tough question because I talked to Josephine yesterday. We are helping a lot the turbulence model with the mesh adaptation. That means it's unfair to speak about it because if you look, for example, for C-square with a cylinder, we maybe look at the the mesh. If you look at it, it's like well beyond what Spartan armors need. So that's why we're killing the possibility of the solver can interfere on the sensitivity. So I didn't try it without that much because we have these tools. But you're right, it could be. But maybe you will say, this is my final shape in respect to this computational cost. If you want to increase the computational cost, I can have maybe different shape because it's looking for more details in the flow. But really, having a VMS approach, which is a type of ELS, coupled to a Spartan armors when it's needed, with this kind of meshes, I'm beyond what the precision could interfere.
Okay, thank you. And my second question is, Have you already, or do you plan to test the fitted models in experimental settings?
Yes, very good. I tried something very nice. Well, we call it ballotage, sloshing. Okay, if you have a cup in your hand, okay, the sloshing is like if you move your hand, the water inside the cup should go this side or this side and goes out. Okay, and this is very important for maybe the reservoir of Formula One or a tank, big tank on the truck, or even for a not for a fusee, for a like when you go to the moon with the engines. So we have designed a laser that look at the cup or at the tank that we have from above, okay, and evaluate the movement, and when the water is going to go out, or the milk, we use the milk, so the movement, the robot will change its direction. So you start with a push, and the water start changing, and the robot or the hand that we have should react in the opposite direction to keep the milk inside the water tank. So this is one example, but the environment, yes, could be experimental, and this is one of the examples that we tried.
Okay, thank you very much.
Thanks. One small question. Have you compared the results in terms of computational effort with sort of a joint solvers?
Very good. Yes. On one of our paper on the simple examples, comparable. If you are really low Reynolds number and very simple example, maybe the adjoint it's better. The moment that your situation is average complex or complex, okay, you can beat. It's very advantage to use the deep reinforcement learning. And we showed on some examples, analytical one, you know, that you can use analytical solution to, you know, the optimization, and then you can compare. On simple example, we are comparable. Sometimes maybe we cost a little more, but whenever your situation or your flow, or it's a little bit average complex or more complex, there is no go with it. Go with the deep reinforcement learning. This is what our finding. Maybe okay. We'll take a small break, and then we will hook with Jonathan.
Eli, may I just interrupt? The micro went on sleep mode. I think there was one more question.
Sorry.
Yeah, one question. Have you tried with varying Reynolds number with application to say wind turbines, as you mentioned, and you might result in flatback aerofoils? Is that the case?
We didn't go with the varying, but we find a very weird. Like we were working on the space between them, on the length. We allowed the length of the wind turbine a little bit to move, and on the curvature of all of them. We find out that the space is important, but it was for a fixed real number, because we had one situation. We have a wind turbine like a experimental channel that has a certain velocity, and we use that, but we didn't vary as you. However, this example, you're saying something very similar. We tried a high Reynolds number for a symmetric wing, and we were asking it minimum lift. So in this case, it will give you zero angle of attack. But what you're saying is, like, if I want a minimum and it has a plate, we didn't try it because we didn't change. We don't have an application in this case, but it could be fun to try it.
Yeah, thank you.
Okay.
One more question, Eli. Sorry.
Yes.
Hi, could you address how well does the DRL-based shape optimization scale with the number of design variables?
Yes. that means how many control point, if you want to take in your domain, in your shape, right?
Indeed, yes.
We didn't do this, but we were surprised that it's funny. We tried a appendix on a car. Okay, the left, behind the car, this how we call it, the rear wing, if you want, and the number was 12 in this case, and we didn't see a lot of like interference. We didn't look like that on this in complexity. We were obliged to do 12 because the geometry of the wing was complex. You know, there is some part from this side, there is some part from this side, and there is there is two parts even for it. But we didn't like look at it in a complexity way, how we're gonna increase or decrease, because we needed this 12 because we had different parts in geometry. But you're saying now, if rather than taking 5 as in picture here, I take only 4 and I compensate with the function between them, what will happen? This is a good way to try it. We didn't try it yet.
All right, thanks. Okay, so Eli, thanks very much. You suggest to have a break now. I think officially we don't have, but
okay. I just to catch Jonathan and he connect. Just
yes,
5 minutes.
Okay.
I'm here.
Ah, you're here because
Yes.
I cannot see you on the list. What is your name on the list?
Jonathan Vicra.
I didn't see it.
But
Now you see it. Now it's it.
I'm registered as a guest, so if you
okay.
want me to.
Yes, thank you, Jonathan. I think you heard some part of the discussion and the question.
The end, yes.
Very good. Okay, so I will stop sharing. Try to share to see if it's work.
I need to have the authorization. I think I don't have at the moment.
I can try. What is your name?
Jonathan, Jonathan Vicra, Viqera.
Yes. See you.